Welcome to today's video. Today we start the last part of the course, which is the introduction to PDEs. We're going to learn to solve, at least we're going to learn one method to solve PDEs, and we're going to apply to three of the most important PDEs that a beginner in the art of PDEs gets to see. All right, so we're going to learn there are many methods to solve PDEs. The method that we're going to learn is one very powerful method for linear equations, but it's called separation of variables. Separation of variables was first developed by Fourier. Remember about Fourier's problems with heat when he was in Egypt during the Napoleonic invasions of North Africa? Well, Fourier developed these methods and also the Fourier Series, trying to understand the propagation of heat. So one of the equations we're going to apply is actually the heat equation. The heat equation, which is also called the transport equation because it's similar. Keep in mind we're going to see the heat equation in one dimension. So imagine that the heat equation tells you about the propagation of heat, of course, in a material by conduction. We know that there are three ways in which heat can propagate, roughly speaking. One is radiation, the other one is conduction, and the final one, convection. Radiation is by emission of electromagnetic radiation. All bodies at all finite temperature emits electromagnetic radiation, right? You've seen metal being heated, and then the metal gets red and glows, and then if you keep heating it, it gets white. And that's because it starts emitting first at room temperature like we are emitting in a distribution of all frequencies, but mainly peaked at the infrared. If we increase the temperature, like we do with iron, for example, with steel, then it gets red, so the peak of emission gets closer to the red, and then if you keep heating, when you heat it, the peak of emission moves to the green. When it's in the green, it doesn't get green because the tails, the peak of emission is not one frequency, it emits in all frequencies around it, so you see it white because it's emitting lights in all colors around green, which is all the spectrum, right? Anyway. There's some curiosities that we can talk about, and we will talk about in the review sessions, about colors and about electromagnetic radiation and heat if you want, as in brown and magenta. Those are not real colors, they don't exist. Magenta is my favorite color, and it's mainly because it's in the brain only, it does not exist. It's not associated with one frequency of the electromagnetic spectrum. We will talk about those things perhaps if you're interested in the review sessions. Those here are really amazing stuff. It's kind of really cool, and in a way allows you to relate the material you see to super cool, interesting aspects of the physical world, right? That we try to understand with those mathematical models. Now, radiation is about that. It's emission of electromagnetic radiation by bodies that are hot. When they're hot, they emit radiation, okay? That's what happens when you heat up a body. We are all hot. We are at a pretty much about 37 Celsius temperature, so we emit electromagnetic radiation, we radiate away. So that's the sun, and that's why we get heated by it. Now, for sure, the sun is a much more hot material than we are, okay? So obviously, the sun is emitting not only way more energy output, it emits at a higher frequency. Not only a lot of amplitude, but also a higher frequency of emission than us. Anyway, another method of transmission of heat is conduction. Now, conduction and convection are often confused, but they both explained by this kind of equation, in a way, or modeled by this kind of equation. Let's understand them, right? Conduction, right, because conduction and convection tend to happen simultaneously most of the time. In a solid, it's mainly conduction. In a liquid, it's both. In a gas, it's dominated by convection usually. Now, convection and conduction. Both of them is transmission of heat from one area to another area that form the material medium that you are. Now, in conduction, basically you get molecules that are hot and are vibrating, right? And because they're hot, they hit the molecules next to them because of collisions, right? The hot molecules collide with the molecules around, and the heat itself is transported in a way. Or it could be the energy is transported like that. Or it could be that the hot molecules physically move where the cold molecules are, and they replace them, and that is convection in a way. Now, convection is another particular phenomenon of something more general, which is advective phenomena, which is when, like diffusion, osmosis, concentration propagation, when you add a little bit of dye somewhere and the dye distributes in a fluid, right? That is also an example of a phenomenon that is described by this kind of equation. Now, we're going to see the simplest equation, which is only two variables. So that means one spatial dimension and time. Well, we say 1 plus 1, d. 1 plus 1, d, heat equation. Which means two dimensions, one of them space, one of them time, okay? Now, what is that physically? Well, UTX, if we think of it as a heat equation, it could be modeling the temperature in a metal bar, for example. And then you put the extremes in ice or something at a constant temperature. And then imagine that this is hot. It's a hot bar, but the hottest part, it's hot because it's getting friction in the middle. So the temperature at the beginning is like that, very high in the middle and low at the borders, right? And then we let it evolve. What would happen? Well, the heat probably here will move this way and then maybe cool down if we keep this at a constant temperature and so on and so forth. So what will happen with that? That is dynamical. You see, this is U has a dependent on x, but at every point in x, it has a dependent on time. It changes in time at every point. So it's two variables. It's changing in two variables. Changes in space, also changes in time. Okay? All right. That's the form of the heat equation. It's interesting enough, first order in time, second order in space. It's a second order linear equation, and as written is homogeneous because there's no independent term. Okay? All right. The second equation we're going to know how to solve is the wave equation. The wave equation is very similar, more or less, to the heat equation. The difference is that this is second order in time instead of being first order in time. The wave equation describes oscillatory phenomena. In the variant that we wrote here, which is a 1 plus 1 d wave equation, one dimension in space, one dimension in time, it's describing the vibrations of a string. You see, we have a string that is oscillating like that, and u is the amplitude of oscillation, and the amplitude of oscillation, of course, depends in time. Every point will oscillate in time, but also if you move from here to here, it oscillates as you move in space. So it depends both in space and on time. Okay? The wave equation is very important. It describes all sorts of oscillatory phenomena, transmission of electromagnetic waves, describes vibrations of strings, and mechanical waves of any kind. Of course, the wave equation gets more complicated in higher dimensions. Here, because it's the first time you see them and it's an introduction, you're going to learn how to solve it in 1 plus 1d. All right? Before learning the complicated stuff, you need to learn the basic stuff. All right? So we're going to solve a lot of strings. Like when you do string theory. If you're interested in string theory, you can ask me in the review sessions as well. All right? All right. The third equation we're going to learn how to solve is Laplace equation. Now, Laplace equation looks a lot like the wave equation with a difference. There's a plus sign here and another difference. The two variables are spatial variables, so it's a two-dimensional, not 2 plus 1 or 1 plus 1, two-dimensional, two spatial dimensions equation. It's a second order equation, second order in both in x and y, and the difference between the plus and the minus, well, is important and is there. The difference is that the signature of the two variables is the same and here is different. If you want to ever talk about space-time and a little bit of relativity, if you ever learn that, we can discuss a little bit what makes time special in space-time as compared to spatial dimensions, and how the signature of time has something to do with that. Anyway, in any case, we're going to, right now, to just focus on the equation and what it means and what it could be. So this equation is important because it appears in gravity, it appears in electromagnetism. In electromagnetism, more often, what you would see is something called the Poisson equation. But the Laplace equation is a simplification of the Poisson equation when there are no charges inside a region. Okay? So we have a region without charges inside, but we have boundaries where we can put charges and have electric potentials, right? And then we know that the electric field is the minus gradient of the electrostatic potential. And then, well, you know the gradient is what you get when you apply to the potential. You apply the operator nabla that you saw in your vector calculus, which is x component takes partial derivative with respect to x, y component takes partial derivative with respect to y. So electric field is minus vector, it's a vector, partial derivative of v with respect to x, partial derivative of v with respect to y. Now, we have Maxwell Equation. Maxwell Equation tells me that the divergence of E, so nabla dot E, is equal to 0. But if I write it in terms of the potential, I get that the nabla square of the potential, that's called the Laplacian of the potential, nabla square of the potential is equal to 0. Well, this U could be that potential because this equation is precisely nabla square. Take nabla again here. So if I take nabla dotted with partial v, partial x, partial v, partial y, equal to 0, what I get is, well, this thing is partial x, partial y, so I get the second derivative, v partial x twice plus second derivative, v partial y twice equals 0, which is Laplace equation. All right? Now, Maxwell equation tells us that this is equal to rho, even when there's an electrostatic case, right? So, rho being the density of charge inside. Same would be with the gravitational field. We have the gravitational potential and the gravitational field, and you will get the same, and rho is the density of mass, the mass density inside the region. When it's 0, both the electrostatic potential and the electromagnetic and the gravitational potential satisfy a Laplace equation. So typically, you have, imagine a capacitor or something in 2 dimensions, a very flat capacitor in a very flat region, doesn't allow the field to leak in another dimension. And then you get some distribution of potential here, some distribution of potential here, some distribution of potential here, and then you want to know what is the distribution of potential inside the capacitor at some distance from the plates. Very useful to know, as you may imagine if you're an electrical engineer. All right, so these are the 3 equations that we're going to learn how to solve, and the method that we're going to learn to apply, it's called separation of variables. Now, what is separation of variables? Separation of variables conceptually is really simple. It says, it basically relies on the fact that, well, let's make an ansatz, and let's assume that the solutions, I mean, the solution may be very difficult, but let's try if the solutions can be the product of a function that depends exclusively on t times a function that depends exclusively on x. So we call capital T this function that depends on t, and capital X this function that depends on x. Right. If it's x and y, same thing. We assume that the solution would be a product of 2 functions that depend only on 1 variable. Now, will that work? I can tell you already yes. Can you prove that that's the only solutions that you would have? And the answer is actually yes, but proving that kind of thing is beyond the scope of the course by quite a bit. So the way we're going to approach it is like, well, let's try if it works, math will tell me, as usual when you make an answer. If it's incorrect, math will tell me. If it's correct, math will tell me what the solutions are. All right. So after this brief summary, let's begin with the heat equation. All right, so we have here the heat equation, and we have, so the problem that we have at hand is, right, consider a bar of metal, for example, and I keep the 2 extremes at 0 degrees. I mean, imagine there is a Celsius scale here, and I'm having the ice at the ends of the bar, okay? Now, that means that for all times, at this point, at x equals 0, and x equals L, L is the length of the bar, okay? This bar has a length L, then the temperature at that point is always 0, and at this point is always 0, because it's in touch with the ice. And then initially, I have some distribution of temperature. Now, the distribution of temperature here is given by the cosine, it's an f of x, some function. That's the distribution of temperature, that's f of x. We're going to solve it in general, but also I give you an example that we're going to solve of initial condition, which is, what if the distribution of temperatures is the cosine of 2Lx times the sine of 2L over Lx, right? To give you an example, so something like that. Temperature is distributed like that. Of course, that's not stable. When you start time, right, the temperature is going to homogenize. The hot regions are going to cool down, the cold regions are going to heat up, and then everything is going to eventually, I mean, if we know what's going on, eventually what will happen is that in enough time, the temperature will be 0 everywhere, right? Because the extremes are on ice and there's no other source of heat or anything. So we have some initial heat in the bar, this oscillatory function, but in the end, it's going to all equilibrate to the temperature of the borders, right? If the difference between the borders, if the borders were at different temperature, then it would not be on 0, right? It would be a gradient of temperature from 0 to whatever temperature, and we will see that case. But if both extremes are at 0, we would expect that whatever the temperature is, it will evolve in time for a while, but eventually it will all fall to 0 in the whole bar. And it will start being 0 here, rather than something like that, relaxation like that. All right, well, let's solve the equation and see what happens. Now, separation of variables. Remember, what we do is we assume that u of tx is going to be a product of t and x of x. So this is the ansatz that the solution is going to be a multiplication of a function of strictly t and a function of strictly x. All right. Now, if that were the case, then I can write the equation like that. I can write the following thing. X on one side of the equation. Well, let me write it like that. I plug in, the first thing that I do is I plug this into the equation, okay? And I get the following. So let's just write it here. I'm going to write it here and then erase it, but let's write it here. So I have partial u, partial t. What is that? Partial u, partial t is going to be, well, if it's this, it's t dot of t times x of x, right? And then partial u squared, partial x squared is going to be, well, t of t and then x dot dot of x, right? Because the derivative with respect to x jumps over t, the derivative with respect to t jumps over x. I only differentiate t. So if we substitute in the equation, if we substitute these two up there, we get the following, right? This is the equation, and then we substitute this in 1, what do we get? Well, on the left-hand side, let's just write the whole thing. T of t, x of x, equals kappa t of t, x dot dot of x. All right. Now, we can rearrange this and write all the x's on one side. For example, x dot dot of x divided by x of x. All right. I put them both on the right hand side, but then I write the other. So I put this one here, and I put all the t's on the other side and the kappa also on the other side. So that would be 1 over kappa, and I get t dot over t divided by t of t. That comes from equation 1. So equation 1 plus the ansatz that u factors into a function of only t and a function of only x gives me this equation here. Why do I put the kappa on this side? Well, it's usually convenient to put the kappa where the fewer derivatives there are. If you want a constant, just package it with the part that has the fewer derivatives to make it simpler. But it's indifferent. I could have done it on the left as well. All right. Now, we need to realize of something clever here. We have on the left a function of only x, right? And on the right, a function of only t. Do you agree? All right. And this has to be true for all values of x and t. Because it comes from the equation, it has to be true always. Now, it could happen that for some values of x and for some values of t, you get a 7 here, and there's some other value of t for which you get a 7 kappa here, and then they coincide. But that cannot be true for all values of x and t, unless this thing does not depend on x, and this thing does not depend on t. That's the only way. The only way a function of only x can be equal to a function of only t is if the two functions are constants. Doesn't depend really on x. Because otherwise, varying x will separate me from this because that doesn't have any x. And varying t will separate me from this one because this one doesn't have any t. So they cannot have any t or any x. All right? So that tells me the second derivative of x divided by x and the first derivative of t divided by t have to be constants, not functions of x or t. And we call that constant lambda. And that lambda, we call it, we're going to see that it corresponds to eigenvalues again. Christ lambda. But we're going to call it the separation constant. Sometimes I may even say eigenvalues, but forget for now, and this is called a separation constant. You see, I hope that this is understandable. This is something that people sometimes trip over the first time, but quickly understand. Everybody quickly understands when you see it like 3 or 4 times. Reasoning again. On the left-hand side only a function of x, on the right-hand side only a function of t. The only way they can be equal is if neither of them depend on t or x. All right? And that means that they're a constant, and I call this constant lambda. All right. So let me write this equation here. That tells me that x dot dot divided by x of x of x, it's equal to lambda, but also 1 over kappa t dot of t divided by t of t, it's equal to lambda. So I have 2 equations. All right. Let me erase this. Hopefully now that is understood. So now that we have these 2 equations, let's write them separately. So this thing yields 2 equations, right? Reading this one, we get x dot dot of x minus lambda x of x, this is a capital X of course, equals 0. All right? And on the other hand, we get that t dot of t minus kappa lambda t of t equals 0. Now, this kappa is a constant, is the conductivity actually of the material, the thermal conductivity of the material. All right, so these are 2 equations, and these 2 equations, we know how to solve. They're pretty simple. The second one, it's very, very, very simple. It's a first order equation. And not only is a first order equation, it's a separable first order equation. Let's quickly solve it. So that I get, let me just write it again, t dot of t divided by t of t, it's equal to kappa lambda, all right? And that means, you know, I integrate both sides, I get a log in here. Let's just write it, log, this means log of t, it's equal to lambda, lambda kappa t, lambda kappa small t, right, plus some constant, let's call this constant, I don't know what I would call it, I call it here w tilde, so for example, w tilde, and then that means that t of t would be some constant, let's call it d, e to the lambda kappa t. Now this constant is not going to be so important because we're going to reabsorb it in another constant. You see there, this is a product, so the constant of integration here, I can reabsorb it in the other function. So let me, for simplicity, take this d equals 1, that I can in this case, and write this as e to the lambda kappa t. All right, this is, again, there would be an integration constant, but I'm going to reabsorb it in another integration constant that appears on the x. All right. So nice, we already solved the t. We need to solve the x. Now, if it were so simple, I wouldn't have left that much of a board and made an effort to write up there. So yeah, there may be some complication to it. Now, the first equation we also know how to solve is a second order linear equation, homogeneous of constant coefficients. So we need to write the characteristic polynomial. Because we have already used lambda here for the separation constant, we're going to use m for the variable in which we write the characteristic polynomial. So the characteristic polynomial for this, let's write it, characteristic polynomial is m squared, lambda squared, right, but lambda we've already used, minus lambda, and then, okay, that's right. That's the characteristic polynomial. And then to find the roots, so roots, to find the roots, you want the solutions of this equation. Okay? So that means that lambda is equal to m squared. All right? Or in other words, much better, m squared equals lambda. Okay? So m squared equals lambda gives me are the roots of the characteristic polynomial. Now, the roots are m squared equals lambda. It could be plus minus lambda. It could be, remember, it could be complex conjugate pair of roots. It could be a double root. It could be many things. All right? Wonderful. So what we're gonna do now is take this and see all the possible cases that we can have. Because depending on the value of lambda, we will get different natures of roots, right? So let's check the three possible cases that we have. We have three possible cases. Let's just write it here. I need to leave enough like that, let's say. Case 1. Lambda equals 0. What happens? I mean, we don't know which ones. Maybe all of them, because the thing is that lambda is something we need to find. You see, lambda is the separation constant, something that we need to find. So we don't know what it is. So we need to actually account for all possible cases and see which ones. There's a thing with answers. Math will tell us which case is the valid one. All right, depending on the compatibility with the conditions that we gave. Okay, the initial conditions and the boundary conditions. All right, case 1, lambda equals 0. That's simple. If we look at here, we see then that m in that case is just 0. It's a double root equal to 0. M0, double root. All right. Now, remember what happened when we had a double root? We have the exponential of eigenvalue t, well, mt. I mean, it used to be lambda, remember, but now lambda is the separation constant. That's standard notation. So we get the exponential of mt times a polynomial mt. Mx, in this case, it is an equation on x, right? Exponential of mx multiplying ax plus b, right? Now, in this case, m is 0, so the exponential of mx is just 1. So that means that the solution is x of x, it's equal to a constant ax plus b. And there you see why I didn't write the integration constant here. Because this constant d in here, because x of x is going to appear multiplying t of t, I can redefine my arbitrary constant that will be fixed by the initial conditions as the multiplication of this constant that appeared here with the d in here, okay? And reabsorb it in there and save for the b. That's why I didn't write the integration constant here, because I write the constants in here. All right, now, wonderful. So in the case lambda 0, we also know what t of t is, right? That's x of x. But then t of t is equal to, well, I go here and substitute. And if I substitute lambda is equal to 0 in here, I get that t of t is just 1. So we get a stationary solution. What does it mean, stationary? Stationary solution. What does that mean? It does not depend on time. If you are in the case lambda equals 0, the solution will not depend on time. T of t is 1. All right, so the solution I can write already. It's very simple in this case. U of tx, the final solution, the product of the two, is just ax plus b. Of course, I will need to impose the initial conditions to find out a and b, and to find out even if this is the case we are in. So we underline this, which is the result in case 1, and let's check case 2. Case 2. Case 2 is when lambda is larger than 0, something that could happen, right? We don't know yet if it's the way it would happen. Now in that case, what we know is that, well, m is equal to the square root of lambda, right? But before we do that, let me rename lambda, let me define here lambda, let me rename it as omega squared. We know that lambda is positive, so it's the square of something, right? So let me call that something omega. This is going to be very convenient later, and it can also suggest some sort of frequency, we will see, okay? Okay, lambda is omega, and that means that m is equal to plus minus omega. Two real roots. We know from our second order linear ODEs of constant coefficients that when we have two real roots, the solution is going to be some exponentials, right? And then we get that x of x is a times the exponential of the first eigenvalue, the first root, which is positive omega x plus b exponential of the second one, which is minus omega times x. That's the solution. And now we can take and write t of t, substituting lambda by omega squared t of t. We know that this is equal to e to the omega squared kappa t. And that means that the total solution, the solution to the equation, in this case, if lambda were larger than 0, would be u of t comma x equals, well, the two of them multiply, a e to the omega x plus b e to the minus omega x multiplying e to the omega squared kappa t. All right? Now, if the conductivity is a positive number, which it is, you'll see how this thing is it's an interesting solution because it looks like the temperature would exponentially go up with time. So maybe not a realistic case that we consider, but certainly a solution of the heat equation, okay? We will see, we will see. We need to consider all of them. We're asking math, are there any solutions like this? And math is telling you, yeah, actually, yes, but depending on what your separation constant is, they will be different. Now, it's not up to math to find the separation constant, it's up to us. So, alright. Now, case 3. Case 3. Lambda is less than 0. Now, if lambda is less than 0, let me write lambda as minus omega squared, right? Because if lambda is negative, then it's certainly minus something squared, which is always positive. So I call it omega. Now, in that case, m, which is, of course, the square root of lambda, would be equal to plus minus I omega. I get a pair of complex conjugate roots. And we know what the solution is like for a linear ODE of constant coefficients. It would be exponential times the real part of the eigenvalue multiplied by the cosine plus the sine of the imaginary part times t. Now, there's no exponential case in our case because there's no real part. So it's just the solution in this case, as we learned in the topics on ODEs, check the card, that may or may not exist. Sorry about that. It's a cosine of omega x plus b sine of omega x. And you see why we call it omega. It's kind of a frequency in a way, right? Anyway. So we know, substituting, of course, that t of t, oops, I wrote it again. It's the exponential of minus omega squared, which is lambda, substituting lambda in this case, kappa t. And that's much more reasonable. Somehow this is going to kill the temperature in time. I'm just making comments, huh? Math doesn't really tell you which one is the right one. You have to be clever about it. All right, the total solution then in this case, in case 3, would be the product of the two. So it would be a product of a cosine omega x plus b sine omega x times e to the minus omega squared kappa t. All right. This is kind of cool because let's recap on what we've done here so far. We asked math. Okay, math. Somebody tells us, I have a problem. What? I have a bar. Okay. It's hot. Okay. And I want to know, I put the extremes on ice, and I want to know how long it's going to take and how it's going to cool down and what's going to be the profile of temperatures as it does it. You see how powerful this is? We're going to learn the profile of temperatures for all times. All right, cool. Then you say, okay, do you know the conductivity of the metal? I say, yeah, I checked it on a box or I measured it or whatever. It's something, this amount. Cool. So if you learn the conductivity of the metal, then you put it in here, and let's solve this equation. Wonderful. So if we solve that equation, then how do I solve it? Well, let's ask math. And we ask math. Okay, is the solution like that? A function of t multiplied by a function of x? And math says, well, no, I mean, let's see. And then math tells you, all right, if it's like that, then you have these two equations. There's a separation constant. Remember, we've got a function of x equal to a function of t. The only way that can be possible for all x and t is that it's equal to a constant, and that gives me two equations, one for the x and one for the t. How nice. I simplified the problem of the PDE that I had to a problem of two ODEs. Isn't that cool? Now I know how to solve the ODEs. This one is separable, super simple. And this one is a second order ODE, linear constant coefficient, also super simple. Depending though on the values of the separation constant, math tells me, your solution is going to be very different. If your separation constant is 0, it's going to be like that. If your separation constant is positive, it's going to be like that. If your separation constant is negative, it's going to be like that. And what's the value of the separation constant? Well, I don't know. What do you ask me? I'm just math. I am a system of structured logic of statements that connect to each other, and based on actions, I derive consequences and theorems. Well, I don't derive them. I make them exist. You derive them. You humans. So you humans are responsible, or as humans, we are responsible for finding the separation constant and knowing in which case we are, knowing the exact value of this omega, and knowing the values of the coefficients here that satisfy these initial conditions and boundary conditions. Those are boundary conditions, conditions at the boundary, and this an initial condition at t equals 0. Alright? Alright, so what we need to do is apply, first, we're going to apply the boundary conditions, because the boundary conditions will allow us to quickly figure out in which case we are. Alright? And maybe even find the separation constant. Alright. Let me write a little horizontal line so we know that we finished finding the generic solutions in the 3 cases. Alright, so let's impose the boundary conditions. Now I need to organize the board space well, because there's a lot to write and I want it to fit on the board, not to have to erase anything for clarity. Alright, so if we impose the boundary conditions, then we begin with case 1. So let's do case 1 here. Case 1. And I'm going to box them probably blue when I do them. Case 1. So in case 1, we're going to impose the 2 boundary conditions are u of t, 0 equals 0. And the other one is u of t, L equals 0. Alright, I have the solution in case 1. I have u of tx is ax plus b. So the first one, wherever I see an x, I write a 0. So a times 0 plus b equals 0. Nice. That tells me that b has to be equal to 0 to be compatible with those boundary conditions. What about the other one? The other one tells me that a times L, whenever I see an x, I write an L, plus b equals 0. But I know that b is equal to 0. So applying that, I get a times L equals 0. The only way this can be 0 is if L is equal to 0, which is not, because my bar has a length, it exists. So the only possibility of these two things is that a is also equal to 0. So b is equal to 0, a is equal to 0, means that u of tx is just 0. X of x is equal to 0 and multiplied by t is also 0. So this is the trivial solution. Let's call it trivial solution. So there are no physical solutions that, so the only solution here the trivial solution here was that the bar started at temperature 0 always, and we know that's not the case because when we introduce the boundary condition, the initial conditions, we know that it's some distribution, and in fact it's going to be this constant sign. So this one is incompatible with initial, let's write IC, with the initial condition. Okay? So case 1 is not our case. We know that our separation constant lambda is not 0. Wonderful. Let me box this result. Case 1 is not our case. Alright. Let's see if I can do case 2 around here. Case 2. Same as before. U of t, 0 equals 0. U of t, L equals 0. Alright. Now we know what the solutions are like. The solutions are exponentials like that. So let's just substitute. The first one, wherever I see an x, I write a 0. The first one tells me that a e to the omega 0 plus b e to the minus omega 0, it's equal to 0. So that means that a equals minus b. Alright? A plus b equals 0, so a equals minus b. Now we do the same, but now we take A, whenever I see an x, I write an L. E to the omega L plus B e to the minus omega L equals 0. Now, using from the previous one that A is equal to minus B, we get that A multiplying E omega L minus E minus omega L is equal to 0. Just substituting and taking common factor the A. Alright, so let's see what is in here. We have here the exponential of something minus the exponential of minus something. That is the hyperbolic sign, the change. Remember, let's a little parenthesis to explain that function because that's helpful. Remember the sign of x? That was e to the ix minus e to the minus ix divided by 2i. Well, the change, the hyperbolic sign, is exponential of x minus exponential of minus x divided by 2. Alright, so it's very similar to see the construction, right? The change is to the exponential when the sign is to the complex, the imaginary exponential. Alright, so this function change is very cool to understand because this function, if we plot it, what is it like? Well, let's see. In the positives, as it grows, this one gets exponentially fast, and infinity goes like an exponential, and this one decreases very fast, exponential. So this one is negligible really fast. This one is the one that dominates for the positives. Now, for x equals 0 is 1 minus 1, so it's 0. We know it starts here, and then it grows exponentially fast. And what does it do for the negatives? For the negatives, well, it's the opposite, right? This one is the exponential of something negative that grows, which goes to 0 very fast, and this one dominates. This one is the exponential of minus something that grows. So grows to infinity to minus infinity because the minus here exponentially. So what it does is this. Symmetrically, right? And we see how it's an odd function, right? It's supposed to be the same curvature though, on both sides. All right, that's the change. So then we realize that it's only when 0, the change is only 0 when the argument is 0. All right, so let's write this. So this thing, let's write it, no, I don't want to separate it. This thing means that A times the change of omega L equals 0. So there are two options. Either A is equal to 0. In that case, if A is equal to 0 because B is minus A, then we know that U of Tx has to be equal to 0. That's the trivial solution because x of x is equal to 0. So same as before, that's incompatible with the initial conditions. The other possibility is that omega times L equals 0, which means that either omega is 0 or L is 0. So this one is incompatible. We have a finite length bar, we really have a bar. This is not, it's inconsistent. Let's write inconsistent. Why is inconsistent? Because we are in case 2. Case 2, lambda is larger than 0, which means that omega squared is larger than 0. And if omega squared is larger than 0, it cannot be equal to 0. So this is inconsistent. I'm going to try to write it better. Inconsistent. And this one is incompatible. And this one, it's also incompatible. All right. So, why did I do that? Let's quickly erase this. And then we found that there are no solutions to this problem coming from case 2. Aha! So math is clever. Math has told us that there are no solutions coming from case 1 where lambda is 0, and there are no solutions coming from case 2 when lambda is larger than 0. Which physically makes sense. Maybe you would have anticipated it, because otherwise we would have gotten here something that grows exponentially in time and probably not very physical for the problem that we have at hand. There might be other problems where something like that is physical, not this one. Not this one. Okay. Great. So the only case left is case 3. Let's go with it. Case 3. Now on case 3 we do the same routine. U of t0 equals 0, U of TL equals 0. All right. Wonderful. Now we substitute whenever we see an x for the first one, we write a 0. So we get a cosine of omega times 0 plus b sine of omega times 0 equals 0. What does that mean? Well, that's easy. The cosine of omega 0 is 1 and the sine of 0 is 0. So we get here that a is equal to 0. All right? Wonderful. Now the second one tells me, the second one says that a cosine of omega L plus b sine of omega L is equal to 0. But because I know that a is equal to 0, that means that b sine omega L equals 0. All right, two possibilities, same as before. Either b is equal to 0, but that yields a equals to 0, b equals to 0, so this is the trivial solution u of tx equals 0, which we know is incompatible. All right. The other option, though, is that the sine of omega L is equal to 0. All right. Wonderful. So if the sine of omega L is equal to 0, that allows me to find a condition for omega. This means that omega L has to be, well, omega L has to be a multiple of pi, right? N pi. Why? Because, well, for n equals 0, omega L equals 0, definitely that's 0. For pi, it's 0 as well. 2 pi, 3 pi, 4 pi, that's when the sign cancels. So that means that I found a value for omega, putting everything on the other side. Omega is equal to n pi divided by L. But you see, this omega is an omega sub n. There are many, there are as many as integers. Oh my God, as many as integers. So n is an integer. And that means there's an infinite number of solutions. Let's write those solutions. So those solutions are, let's write it, u sub n tx is going to be equal to the x sub n. What is the x sub n? X sub n is, remember, a is 0, and then is b sine omega L, but b sub n, because it's one constant per each of the solutions. B sub n sine of n pi over L x multiplied by the t. Where's the t? Where's the t in this case? Yeah, case 3. T is e to the minus omega squared kappa t. So e to the minus omega squared, so m squared pi squared divided by L squared, because that's what omega is, kappa t. And you see, there are many of these, there's infinitely many of these solutions, each of them with their own constant, of course. Now, of course, we know that when you have independent, they're all independent, there's signs with different values of n in here. When they're all independent solutions, the general solution, because it's a linear equation, would be the sum of the infinitely many solutions that are independent. All right? Okay. So the general solution to this equation would be the sum of, this is an element of the basis of solutions. The solutions to this equation form a vector space, and these functions are the basis of that vector space. All right. Now, let's write then the solution, what it's going to be. The solution is going to be u. Okay, then in the space, u of tx, it's equal to the sum from n equals 1 to infinity of bn sine n pi over L x multiplied by e to the minus n squared pi squared divided by L kappa t. This is the general solution. This is not the solution to the exercise, because we need to determine these constants, but this is the general solution that satisfies the boundary condition without imposing the initial condition yet. Now, you may wonder, two questions that you may wonder. First, one that I already answered, but it wasn't that clear. Why is there an infinite sum of them? Well, because we found an infinitely many conditions under which we get infinitely many values of the separation constant. All of them are valid. All of them are solutions to the equation. Now, of course, they're independent. You cannot write one in terms of the others because they have different multiples of the sign and different exponentials. So the general solution has to be the linear combination of all the independent solutions to get the most general possible solution. Okay? What we're doing here is consider the most general possible. We start from super general. Lambda could be anything, and we start excluding cases to make the super general solutions that we have to make them compatible with the boundary conditions so far. Now, another question that you may have is, but you said that this is an integer, and indeed, this is also true for negative values of n. Why do you add the 1 to infinity and not minus infinity to infinity? Very good question. You see, if I were to add minus infinity to infinity, I would be adding the same solutions twice. So it's working extra for nothing. Why? Well, to begin with, the time function doesn't change because the sign of n doesn't affect anything. It's the same exponential, right? Now, the sign of the negative n, you know that the sign is a not function, which means that the sign of minus x is equal to minus the sign of x. So the ones with the n that are negative, the only difference is a minus sign overall, and that I can reabsorb it saying that bn, a new bn, that is the old bn minus the b of minus n. Right? By that I mean that whatever the constant, so the things that multiply the negative values of n are also can be reabsorbed in the constant that multiplies the n, because it's just a minus sign of difference between them. The only difference between n positive and negative in this sum, in these terms, is a minus sign, and the minus sign is a constant that I can reabsorb into the general constant bn that I have determined yet. That's why I have 1 to infinity. If you still have questions or doubts about that, please do not hesitate to ask them in the review sessions that we will have. All right, so there's one more step, and that one more step is determining the constants bn. Okay? How do we determine the constants bn? Well, imposing the condition that I have not imposed yet, imposing the initial condition. All right, so let's impose the initial condition. Wonderful. So the initial condition tells me that, I'll write it here, u of 0x it's equal to f of x. All right, so I substitute here, whenever I see a t, I write a 0. So I get that f of x is equal to the sum n equals 1 to infinity of bn sine n pi l x. So, how do we determine the bn's? Well, really glad you asked, because this connects with something we've seen. This thing is a Fourier series, isn't it? So in fact, the bn's here are the Fourier sine coefficients of the f of x. This is a sine Fourier series, and indeed, this is an odd extension, right, of the f of x. Look at that. The odd extension that we had is look, this is omega x, right? This thing is omega x with the omega that we had. And remember that omega is 2 pi over t, and then this is n pi over l. So pi cancels, and what this tells me is that t is 2l. Indeed, the period is 2l because we're doing, this is the sine Fourier series of f of x. The odd extension of f of x, but the Fourier series that represents it in this region of 0 to l. So all that we need to do is to find the Fourier coefficients of f of x. All right, let's do it. So if we do it, we know that b of x, so b sub n, it's equal. Let's just write the whole thing. 2 over the period integral from minus l to l of the odd extension of f of x. Let me just write f of x as the odd extension, right? Or maybe I'll write dx f of x as the odd extension, then the sine of n pi l over x. Remember, this is the sine Fourier series, so it's the odd extension of this small f of x. Capital F here is what I call the odd extension in this case. I know that I called it h or g in the Fourier series part, but just to make it connected with the f and not confused, we get this. But we know what this expression is. The first thing, well, let's just substitute. 2 over the period is 2 over 2L, right? Integral, and then minus L to L. Well, I know this is odd because it's an odd extension. This is odd because it's an odd extension, so this whole thing is even. So what I get here is twice the integral from 0 to L, same as we've been doing in the Fourier series, dx, small f now, because from 0 to L, the odd extension coincides with f of x sine of n pi over L. That's not a minus or anything, okay. And those are the bn's. Now, if I were to write the general solution for a generic, so if my initial condition was f of x, then I need to find those coefficients the same way we've done in class. We solve the integral and so on, and in the end, the solution, of course, is u of dx is equal. Then write the u. Well, the u is the sum here. The sum n equals 1 to infinity, and then the m is this integral here that you write, right? This integral, you cancel those two. You write the integral in here, and then multiply by the exponential of minus n squared pi squared L kappa t, right? Square pi squared. Okay, but we need to compute this. Now, there are two ways. Let's take the particular case that we have here. The particular case that we have here is that f of x is equal to the cosine of 2 pi over Lx sine of 2 pi over Lx. Now, we can put this into here and do integrals and use the orthogonality of the sine functions to do it fast if you want. But this is one of those that I taught you to do by inspection, right? Because by inspection, we realize that this is the formula for the sine of the double angle, right? So this thing is equal to 1 over 2 sine of 4 pi divided by Lx, right? Agreed? This is a double angle. There's 1/2 of the sine of 2x is equal to the cosine x sine x. All right? Wonderful. So if that's the case, then we compare the Fourier series. So the Fourier series here has so pay attention, this is important. What are the terms of this series? So let's write them. Is b1 sine of pi over L with a 1. I'll write the 1. 1 times pi over L x plus b2 sine of 2 pi over L times x plus b3 sine of 3 pi over Lx plus b4 sine of 4 pi L over x plus all of them. Now we compare. That has to be equal to f of x. So this thing has to be equal to 1/2 sine of 4 pi over L. Let's compare. Okay, terms that go with pi over Lx. None here. Wonderful. So b1 is equal to 0. But so is b2. Nothing goes with 2 pi over L. All right. But so is b3. Right? In fact, what about b4? No. b4 we have it. Sine of 4 pi over L times x is in the f of x. You see, f of x, this is the condition. F of x is equal to this. So we can determine by inspection that b4 it's equal to 1 over 2, just looking at the coefficient, and bn different from 4, it's equal to 0. You see? Okay, again, what did we do? We equated the series to f of x, because that's the initial condition. And then f of x, we manipulated with trigonometric relations to get something that looks like the sine of pi L over x. In most assignments, and if you have an exam or anything like that, I will give you a condition like that, always. I don't want you to do a Fourier series in this exercise because it's too long already. So I will give you a Fourier series that you can do by inspection. You can also do with the usual integrals. But in general, you're not going to have to, except perhaps in a very difficult exercise. But in general, you're not going to have to. So always try to see if you can do it by inspection like that, okay? And then by inspection, what it is? Okay, I wrote this as one of those signs, and I realized that the only term that is here is the one that n is equal to 4. So all the b's that are different from 4 are 0, and b equal to 4, that multiplies the sine of 4 pi over Lx. Comparing, I see that this is a 1/2. That's the solution. All right, so let's write finally the solution to the exercise, the solution to the heat equation that satisfies the initial condition, this profile of temperatures at the beginning, And the boundary conditions that you put on i's, the two extremes, is the following. U of tx, it's equal to, now the infinite sum of all the solutions doesn't have the infinite terms, only the term with n equals 4 is there. So I write the terms with n equals 4, b4, which is 1/2, so 1/2. Now sine of 4 pi divided by Lx, I'm substituting here, only that all the b's are 0 except for b4, that is 1/2. Right? And that multiplies the exponential of minus 4 squared minus 16 pi squared divided by L squared. Sorry about that. The exponential of n squared. Well, n is 4, so 6 minus 16 pi squared over L squared. And that multiplies kappa times T. After all this work, this is the solution to the heat equation that satisfies the initial condition that we gave, that is this cosine sine profile of temperatures, and that the extremes are nice. And look what happens. What happens is that in time, everything is going down exponentially fast over 0, and you get an oscillation in space. So basically, this is going down, the oscillation is kept in space with the same frequency, if this is the condition, and it just goes to 0 everywhere. If it were a solid line like that, you would see it going down and flattening, but because the distribution was that's one of the normal modes of the bar, the heating happens really fast in all places, exponentially fast. You see that different frequencies, if we had different terms, you can tell. If instead of 1v1, we have 1vms, we have 2 vms, you see that different components go down with different frequencies. The larger the n, the faster they go to 0, right? So the high frequencies are killed faster than the low frequencies. So if you have something that is like kind of a constant like that, first you will blur. Basically, you remove the shape. You know, the high frequencies is the information about the shape. When we did the Fourier discussion about the Fourier transform and what it means high frequency versus low frequency. So you lose all the details of the distribution first. It homogenizes, makes sense, conduction, homogenizes the temperature locally. I get in equilibrium with my neighbors more or less. And then we all together go down. That's what happens, okay? In general, you have a distribution that doesn't go. This was very cherry-picked, so it coincides with the normal model bar to make it easier for you to compute the Fourier series. But if it were, say, a Gaussian profile, or something that is easier to integrate. Any other profile that is like that, that's what's going to happen. It's going to first erase the features and then go down. All right, so we've learned that when you have i's at the extremes of the bar, the higher frequencies in the distribution of temperature will get killed earlier than the lower frequencies. Anyway, this is a very helpful mathematical tool, and you can use it from, determining when somebody died to actually building insulation for electronics that you're doing that you don't want it to get hot in a very hot environment, for example. Or that you want it actually to dissipate, to do thermal components that dissipates, radiators and things like that. All right, my friends, that's a heat equation. Let's do another example of a heat equation that is a bit more complicated. Couple of examples of the heat equation, and then we will move to another one in another video. How about that? All right, let's do it. All right, I made it. This is me from the future. This is a whiteboard that I'm gonna write in the future. So here it is. I interrupted the flow of the space-time continuum with my friend Pasmi. I know that Pasmi promised you to have 2 more examples in this video, but I come from the future and it's a horrible future. In that future, the video got too long and then you hated me because of that. So what I'm gonna do instead is I'm gonna split this video into 2 videos, and that will repair the normal flow of the space-time continuum, and you will continue learning differential equations with me. I hope it works, all right? So I'll see you in the next video.